With the publication of the paper by Shimizu, Rajendran and co-workers in Science 2021, there has been a tremendous amount of interest in the use of Calgary Framework 20 for CO2 capture from flue gases under humid conditions. This CO2 capture application has been discussed in several video presentations on YouTube, and the theoretical background is discussed in significant detail in my paper published in Separation and Purification Technology. An important aspect of the CO2 capture using CAF20 is the strong influence of percentage relative humidity on the CO2 capture characteristics for mixtures of CO2 with varying amounts of water vapor in the bulk gas mixture. The mixture adsorption equilibrium is determined to be strongly non-ideal. The experimental data on the mole fraction of CO2 in the adsorbed phase as a function of percentage relative humidity clearly identifies two scenarios for percentage relative humidities lower than about 50%. The adsorbed phase is significantly richer in CO2 than anticipated by the Ideal Adsorbed Solution Theory calculations that are indicated by the dashed lines. On the other hand, for high values of percentage relative humidity, the CO2 mole fraction in the adsorbed phase is significantly lower than anticipated by the IAST. The explanation for the deviations from thermodynamic non-ideality are provided in my paper referenced here and published in Separation and Purification Technology. Watch also a series of video presentations titled Thermodynamic Non-Idealities in CO2 Capture with CAF20. Parts 1, 2, 3, 4, 5, 6, 7 are available for viewing on my YouTube channel. Today, I discuss the application of CAF20 for CO2 capture from humid natural gas mixtures. My presentation today on CO2 capture from humid natural gas mixtures using CAF20 is entirely based on my paper in Separation and Purification Technology that is just available online. This paper discusses the influence of the presence of water vapor in the bulk gas mixture on separation of CO2 methane mixtures. I show here the unitary isotherms of water indicated by the blue triangles. The red circles indicate the data for the unitary isotherm for CO2, and the green squares are the component loadings for methane, and these component loadings are plotted as a function of the bulk gas phase fugacity. The component loadings are determined from configurational-Monte Carlo simulations as detailed in my paper referenced here. I examine the influence of the presence of water vapor in the bulk gas mixture on CO2 methane separations. For the three components, CO2, methane, and water, we can identify three different binary mixtures: CO2 methane, water methane, and CO2 water. For each of these three binary mixtures, configurational-bias Monte Carlo simulations are used to examine the mixture adsorption characteristics. For CO2 methane mixtures, that was a mole fraction of 5% CO2 in the bulk gas mixture. The component loadings determined from CBMC simulations are compared with the estimations of the Ideal Adsorbed Solution Theory, and we note that the CO2 methane mixture adsorption behaves ideally, and there are no thermodynamic non-ideality effects as experienced for CO2 capture from flue gases under humid conditions. Let us now proceed examining the influence of the presence of water on the adsorption of methane and adsorption of CO2. CBMC simulations were carried out to determine the influence of the presence of water vapor in the bulk gas mixture on the adsorption of CO2 and the adsorption of methane in CAF 20. The mixture adsorption data for CO2 water mixtures is shown here on the left-hand side, where the component loadings are plotted against the percentage relative humidity. And we note that the CBMC simulation data show that the IAST provides a very poor estimate of the component loadings in the adsorb phase. Indeed, there are strong deviations from thermodynamic non-idealities that are best emphasized in this plot here, where the mole fraction in the adsorb phase is plotted as a function of the percentage relative humidity. And we note that for percentage relative humidities lower than about 30%, the adsorb phase is significantly richer in CO2 than anticipated by the IAST. On the other hand, for percentage relative humidities higher than about 30%, the adsorb phase is significantly poorer in CO2 than anticipated by the IAST. These CBMC simulations are in agreement with the experimental data for CO2 water adsorption published in the science paper. For adsorption of methane in the presence of water vapor, a similar behavior is detected, as shown by the CBMC simulation results plotted here on the right hand side. These results are reported in my paper that is just available online. The mixture adsorption equilibrium is subject to strong thermodynamic non-idealities. For relative humidities lower than about 30%, the adsorbed phase is significantly richer in methane than anticipated by the IAST, whereas for relative humidities in excess of about 35%, the mixture adsorption is significantly poorer in methane than anticipated by the IAST. The deviations of mixture adsorption equilibrium for CO2 water mixtures and methane water mixtures is attributable to the failure of the requirements of the IAST. The IAST demands that the gas molecules be homogeneously distributed within the pore landscape without any segregation or congregation effects. For mixtures of CO2 and water and methane and water, we have evidence obtained from CBMC simulations to show that the basic tenets of the IAST are violated. I illustrate that for methane water mixtures, considering two different scenarios. First, we consider mixtures with relative humidity lower than about 30%, and we proceed to looking at mixtures with higher percentage relative humidities. Let's start with the scenario at low percentage relative humidities. At very low values of relative humidities, the mole fraction of water in the adsorbed phase is less than about 1%, and the mole fraction of methane in the adsorbed phase is significantly higher and is about 99%, certainly higher than about 90%. An important aspect of the mixture adsorption characteristics is that the methane molecules are segregated from the water molecules, and the water molecules tend to occupy the same adsorption site, whereas the methane molecules do not occupy the same sites as that of water. So we have a scenario in which methane and water molecules are segregated. This implies that the methane gas molecules do not have to suffer strong competition from the partner water molecules, and this segregation leads to significant deviations from the IAST, and the CO2 loadings in the adsorbed phase is significantly richer in that anticipated by the IAST, because CO2 faces next to no competition with the water molecules. The situation changes dramatically with percentage relative humidities in excess of say 35%. In this scenario, the adsorb phase is significantly richer in water and significantly poorer in methane. Methane molecules are forced to occupy the same adsorption site as the water molecules that are subject to strong hydrogen bonding. This implies that methane is subject to enhanced competition with the partner water molecules, and this results in CO2 loadings in the adsorb phase that are significantly lower than that anticipated by the IAST. So at high values of percentage relative humidities, the mixture adsorption equilibrium behaves non-ideally due to enhanced competition that methane has to endure due to the presence of water molecules that are strongly bonded with other water molecules due to hydrogen bonding. My paper in separation and purification technology referenced here also examines the influence of percentage relative humidity on adsorption of mixtures containing both CO2 and methane. The mixture adsorption characteristics is subject to strong thermodynamic non-idealities. This is demonstrated here in these three graphs, in which the mole fraction of CO2 in the adsorb phase is plotted as a function of percentage relative humidity, mole fraction of water in the adsorb phase as a function of percentage relative humidity, and mole fraction of methane in the adsorb phase as a function of percentage relative humidity. For all three guest molecules, two different scenarios prevail under conditions of low relative humidities and high relative humidities. For low relative humidities, both CO2 and methane are subject to lower or diminished competition with the water molecules due to the segregated nature of adsorption. CO2 and methane are not occupied, are not present at the same adsorption sites as the water molecules. The segregated nature of mixture adsorption results in deviations from thermodynamic non-ideality. The ideal adsorption behavior is indicated by the dashed lines. The CO2 mole fraction in the adsorb phase and the mole fraction of methane in the adsorb phase are significantly higher than the IAST estimates due to the segregated nature of adsorption. Conversely, the water adsorption in the adsorption phase is significantly lower than anticipated by the IAST. The characteristic change dramatically for higher values of percentage relative humidity, where the adsorption of CO2 and methane is suppressed due to the presence of water, and the component loadings in the adsorb phase are significantly poorer than anticipated by the IAST. For water, the adsorb phase is richer in water than anticipated by the IAST. The continuous solid lines are the estimates of the Ideal Adsorbed Solution Theory. In a follow-up presentation, I will discuss how the real adsorption solution theory is to be set up for ternary mixture adsorption.